Good afternoon, everyone. Today we have the great pleasure to welcome Dr. Kaihang Shi. He's a postdoctoral scholar in Professor Randy's Nuh group at Northwestern University. He obtained his PhD in chemical engineering under the guidance of Professor Keith Gubbins, co-advised by Professor Eric Santiso from North Carolina State University. Before he came to NC State, he received his degree in polymer science and engineering from East China University of Science and Technology. His main research interests are applying molecular simulation, theory, and machine learning to understand and predict the phase equilibria, transport, and chemical reactions of complex fluids at interface, surface, and in confined systems, and developing novel porous materials for a more sustainable future. He has been working more specifically on the topics of pressure enhancement in adsorbent films for future high-pressure processing and adsorption on heterogeneous surfaces. He has published 15 papers since 2015, summing over 150 citations. He has also contributed a book chapter in Porous Materials Theory and its Applications for Environmental Remediation, named Current Advances in Characterization of Nanoporous Materials, Pore Size Distribution, and Surface Area. He has an open source code named MMOCA, with a multi-purpose Monte Carlo simulation package for molecular systems. And he has been recently awarded with the 2020 James Farrell Outstanding PhD Graduate Award from the NCSU. So welcome, Dr. Kaihang Shi. Thank you very much for being here, and please feel free to start your talk.
Okay, thank you so much for the introduction. Let me share my screen. Okay, does that look good? Okay, so first of all, I would like to thank Fred for inviting me, and of course, thanks for Keith for suggesting me for this seminar. It is my great pleasure because there are really many role models, the previous presenter in this seminar. So today I'm going to talk about most of my PhD work with Keith. It's on the pressure tensor and nanoscale. So in this talk, I will give you the introduction to the theory and applications of pressure tensor, and of course, some challenges we are facing right now. So to begin with, I would like to give you two examples that is related to microscopic pressure tensor. So what you are watching right now, this is a floating droplet. And the droplet remains a spherical, almost spherical shape. That's because we know there's a surface tension. So the surface tension tells us that the Mother Nature has intelligence to minimize the energy by reducing the surface, the interface between the liquid and the outer space. So the molecule near the interface will pull each other. So the liquid forms a spherical shape. And the surface tension, to calculate the surface tension, we need the microscopic pressure tensor. And the second example is that during the pandemic, at least in the United States, the we call this emergency food or doomsday food is really popular. So this food, you can just open it up and mixing it with water, and you can just eat it instantly. So the production of this kind of emergency food is has to go through the very complicated process. So you can see picture from here that you have to freeze the food and also drying the food. So during this process, some labile biochemical molecules have to experience the stress and pressure inside the solvent. So some molecule will not survive this process, and that will actually affect the final taste and the texture of the food. So understanding the molecule at the nanoscale and the force stress they experience is the key to optimize this entire process. So Pablo Di Benedetti's group has done some many great work on this topic. And this is just two examples of many applications that pressure tensor can be applied. And during this talk, in the later part of this talk, I will give you two examples. So in this talk, I will divide it into two parts. So in the first parts, I will talk about the basics. What is the pressure tensor and why we need a pressure tensor. And we'll talk about the two methods to calculate the local pressure tensor. One is the mechanical route, and the mechanical route is based on the fluid mechanics. And of course, we can derive the local pressure tensor from the molecular, like thermodynamics perspective. And during this process, I will bring up on my personal opinion, that the biggest problem of the local pressure tensor, that is the uniqueness problem. And I will show you how we solve this problem, like in our recent work. And in the second part of the talk, I will give you two explicit examples. The first one is we apply the high pressure, we apply the local pressure tensor to understand the high pressure phenomena in nanopores. And the second example is the collaboration with Carlos Vega, and we apply this local pressure tensor to understand the mechanical profile of solid nucleus. Okay, so let's get started for the first part. So what is the pressure tensor? So pressure tensor, as you can see from the name, it is a 3x3 matrix. And the pressure tensor contains all the information about the pressure that a body element has felt. So for example, the P alpha beta, this is the component in the pressure tensor that gives the force. The P alpha beta, this is the force per unit area in the beta direction, acting on the surface element normal to the alpha direction. So as you can see, you have Pxy, this is the shear component in the pressure tensor, and the Pxx, this is the pressure acting normal to the surface of normal to the x direction, and this is the normal component that we know. And if we are at a stationary system that that's the most common system in the thermodynamics under the thermodynamic equilibrium, only the diagonal elements are non-zero. So like the off diagonal elements, they are zero because they are shear stress, and there's no shear in the system, and they are simply zero. So how can we apply this to the real system? So for the homogeneous system, such as like the bulk gas or bulk liquid, all the components, they are equal. So they reduce this to the bulk pressure. That's the pressure we all familiar with. That's a scalar. But the problem gets very complicated in the inhomogeneous system. And the example I showed you here is fluid inside a slit-shaped pore. So as you can see, the fluid right here, they feel the forces from different directions. So the particle near the surface, they feel the force that's parallel to the surface. So we know the p-axis and py, this is two pressure components that in the direction parallel to the surface. So we call it tangential pressure. And the other direction is the pzz. So pzz is the direction normal to the surface, and we call it a normal pressure. So the tangential pressure and normal pressure, they are different because they acting in the different directions. So what I'm talking about here is in Cartesian coordinates, but most of the time, like in the inhomogeneous system, the pressure tensor in a polar coordinates is much more convenient. For example, to describe the spherical droplets, we probably want to write the pressure tensor in a spherical coordinates. So in the spherical coordinates, there are still three components in the diagonal elements, and they are PRR, and that's the pressure tensor, that's the pressure component in the radial direction R. And we have P theta theta and P phi phi, that these two are the tangential pressure in the polar and azimuthal angle. And if we have a cylindrical shape, such as self-assembled cylindrical structure, or we want to study the fluid inside a carbon nanotube, it's better to write the pressure tensor in cylindrical shape, in cylindrical geometry. So in the cylindrical geometry, we have three independent components in the diagonal elements, and they are PRR, of course, and that's the normal pressure in the radial direction. And we have P theta theta, that's the azimuthal pressure in the azimuthal angle. And we have PZZ, and that's we call the axial pressure because the direction is parallel to the axial x-axis, z-axis. Okay, so in what follows, I will talk about two routes to calculate this local pressure tensor. One is mechanical, the other one is thermodynamic. So from the mechanical route, we know it derived from fluid mechanics, and the pressure tensor can be related to the stress tensor by this equation. So the pressure tensor is equal to the minus the ensemble average of the stress tensor. So the stress tensor is the quantity derived from the hydrodynamics. And you can see it is a function of the position, point R, at time t. So the ensemble average is basically average out the time in the time frame. And the pressure we got is the equilibrium property. And the stress tensor can be written in this form, and the theta alpha beta, and this is the stress component in the stress tensor. And we can see there are basically two terms on the right-hand side. The first term, this is the kinetic term. So the pi alpha, that's the momentum of particle I in the alpha direction. And mi, that's the mass of particle I. So this form we're familiar with from the physics, that the momentum squared divided by mass, that's the kinetic term. And the second term, you see, it's associated with internal energy. And this second term is the configurational term. So the capital U is the internal energy. And this is partial derivative of internal energy with respect to the position of particle I. And we notice that there's a special term in the bracket, that's the line integral. The integral is over a contour C0I. That contour is from point 0 to the point I. So this second part, this line integral is basically assign a force to a space at a point R. But as we know, there's no unique way to assign force in a space. So the line integral here is non-unique. And this is a general form. If we have a pairwise interactions, we can write the second term on the right in this form. The Uij, that's the pairwise energy between particle I and j. And this partial derivative is basically the force between particle I and j. And the contour Cij, that's any contour line you can draw between the particle I and j. So when I say the contour Cij is non-unique, that means you can draw any kinds of contour you want to connect to the point I and j. So here I showed you 4 types of different contours. So the first type is the Irvin-Cook-Hood. So Irvin-Cook-Hood decided to draw a straight line connecting the particle I and j. And this definition is the most common definition people used in literature. And we're also familiar with the Hilashima contour. And this Hilashima contour is composed of 2 components. So you first go from horizontally and then vertically to the particle j. And this is just the 2 definitions. And you can draw any kind of contour you want. And here I showed you some variations of Irvin-Cook-Hood and variation of Hilashima. So this non-uniqueness of the contour reflects the physics that there's no unique way to assign pair force between the 2 molecules to a particular point in space. And this non-uniqueness is not particular to the mechanical route. And our thermodynamic, from thermodynamic perspective, it also suffers from this non-uniqueness. And I will explain to you in following. So now we look at the thermodynamic route to the local pressure tensor. And in a canonical ensemble where the particle volume and temperature are fixed, and there are single components, then we can write the differential of Helmholtz free energy in this way. And the pressure is basically the negative of the partial derivative of the free energy with respect to the volume. So this is the equation we are all familiar with, that we calculate the bulk pressure using this equation. And we can substituting the free energy equation, the A equals to minus kBT log Q, into the above equation, and we can get the following ones. And by by some simple numerical manipulation. So the first term on the right-hand side, that's the kinetic term. So rho kT is just ideal gas term, so it's kinetic. And the second term is the partial derivative with respect to the internal energy, and that's the configurational term. And we know this equation, we can apply it safely to the bulk version, but what if we want to know the pressure at a point? And then, of course, we can extend this bulk version to the local version. So I'm showing you here two equations for a sleeve-shaped pool case. So the equation most part of the local version are similar to the bulk version. And the only difference is that the density rho becomes a local density. So the density now depends on the position z. So z is the position perpendicular to the wall. And the internal energy is also different. So internal energy in the bulk version, it's the internal energy of the entire system. But now the internal energy is at a point z, at a position z. And the equation we are looking at is the tangential pressure in the x direction. So by taking the partial derivative, we keep the length in the z and y direction fixed, and we just take the partial derivative with respect to the length in the x direction, because we are interested in the pressure in the x direction. So it's the same for the normal pressure. So from this equation, so where the non-uniqueness come from? Actually, the non-uniqueness comes from this U, the local energy, UZ. So when calculating local energy, there are different ways to assign energy in the space. So for example, you can assign energy to the position of the two particles, and that's the definition 1 I showed you here. But of course, you can also assign the energy linearly in the space between the particle I and j. So there's different assignment methods for the energy leads to different values for the local pressure. And this actually agrees with the non-uniqueness we just observed in the mechanical route. And if you derive this equation, like writing out this partial derivative explicitly, you will see the final equation you got from the thermodynamic perspective is consistent with the equation from the mechanical route, which is derived from the fluid mechanics. So, so this non-uniqueness problem has a long-standing issue in the field. And here I'm trying to present you the history of the non-uniqueness argument. Of course, the history I presented here is not comprehensive. Like Irving and Kirkwood and Buff, they are the first ones to propose that the local pressure or local stress are non-unique, and there are some ambiguities inside. And in their seminal paper in 1950s, they wrote in a footnote that the local stress is non-unique. But because they are written in a footnotes that people usually ignore it, and people trying to rediscover these things. And in the 1980s, John Rawlinson and Ben Whittam, they discussed this ambiguity of the pressure tensor in their famous book, Molecular Theory and Capillarity. And people like began to realize that, oh, this is really a problem for the local pressure or local stress. And unfortunately, John Rawlinson passed away 3 years ago, and that's a huge loss for our community. And Schofield and Henderson, they also re-derived the equations for the local stress tensor and clearly show the ambiguities involved in the definition. And like people writing papers right now, most of the time they refer to this Schofield and Henderson paper. And after this two important research, and since 1982, like many scientists actually attempt to solve this non-uniqueness issue by imposing additional constraints to the equations. But if you read those papers carefully, you will see there are loopholes and pitfalls in those papers, and there are many mistakes made in the derivation. So this is still an open question in the field. And even though if you look at some application paper, you'll see many papers like reporting wrong results and reporting the wrong equations to calculate local pressure tensor. So the care must be taken when you calculate this kind of local pressure tensor. So we are thinking, like very recently, we are thinking, how is this possible to solve this non-uniqueness problem? So our perspective is that if you look at the differential Helmholtz free energy equation, that the pressure is conjugate to the volume. So if you really calculate a pressure at a point, the volume is infinitely small. So that volume actually doesn't count. So our idea is that possible to construct a coarse-grained pressure tensor? So now you have a volume that really has some number, that a finite volume. So what I'm showing you here is the argon absorbed in a carbon sleeve shape pore. And we divided the system into several bins. So I'm showing you a delta Z1. Delta Z1 is the effective thickness of the first absorbed layer. So we are constructing this coarse-grained pressure tensor, and basically we average the local pressure in this first layer. And we argue that this coarse-grained pressure tensor is unique. That means it has a unique value, no matter what contours or definitions you use. So what follows, I will show you the evidence we provided that this coarse-grained pressure tensor is unique, and also how to obtain this delta Z1. So the figure I'm showing you here is a local pressure tensor. It's the tangential pressure of the fluid absorbed in a carbon sleeve shape pore. So the top panel shows you the local pressure, and the bottom panel shows you the integral of the local pressure tensor. And the background figure is the snapshot of the simulation. So you can see there's only two absorbed layers in the sleeve shape pore, and there are two peaks in the local tangential pressure. And we calculate this local pressure tensor using 4 different contours. So the first one is Irving Kukut, and second is Hilashima. And we also include 2 variations of the common definitions. So these different contours, as I just showed you, are just different ways to assign forces in space, but they are mathematically valid, equivalent. So from this local pressure, the top panel, we see different definitions lead to different local values, and that reflects the non-uniqueness of the pressure tensor. But at the bottom panel, we see if we integrate the tangential pressure, all the contour definitions, they converged at the same points. And we marked the convergence points as A, B, and C. And from the distance between A and B points, we can define this delta Z1. That's the effective thickness of the first absorbed layer. And we can calculate this coarse-grained pressure by averaging the local pressure tensor in this region. So from this bottom panel, we know no matter what contours you're using, this P1 CG has a unique value. So this is the unique coarse grain pressure tensor we are talking about. So some of you may ask that you're only showing 2 contour definitions here, but in principle, there are infinite number of contours you can draw. Is that possible to provide more strong evidence? So we are able to develop a new method to explore the entire contour space. So the central idea here is you reduce a contour in the 3D space to a 2D space. So by taking the integration of the local pressure tensor, we can define a function, Fc, which controls the contour in the 2D space. So the Fc is a function of lambda ij. So lambda ij is the distance between the particle I and the plane Z. And the N and M, they are intersection points of the Z plane with the contours. So this function Fc can be calculated by xin. So xin is the x component of the vector in. Xim is the vector component as the x component of the vector im. And by looking at this equation, we're able to find that this function must satisfy 3 conditions. So first condition, that the function must pass the endpoints, the 2 endpoints. And the second is that the function must pass through the middle points, because the contour, as you see here, the Cij and Cji, the contour, they are symmetric. So they must pass through the middle points. And the function and the condition 3 is that the function must be symmetric, because the symmetry of the contour. So now, equipped with these 3 conditions, we can construct this function Fic freely. If any function that satisfies these 3 conditions, they are valid contours. So what I'm showing you here is that we construct the Fc function by satisfying the previous 3 conditions, and each line here corresponds to different contour definitions. So we constructed the C5, C6, and C7 until C10. There are different contour definitions. And we also included the Irving-Cuckoo definition, Hilashima definition, and the variation of them. And we can see all these functions satisfy our previous 3 conditions. So this basically tells us that we can draw any function that must pass through 2 endpoints and must pass through the middle points, and the function must be symmetric about the middle points. So any function you draw like that is a valid contour. So from this results, we can calculate from the simulation that integral of the pressure tensor. So what I'm showing you here is the local number density on the top panel, and the bottom panel is integral of the tangential pressure, but we only include the configurational part here. So this is argon adsorbed in a carbon sleeve shape pore. So carbon sleeve shape pore was modeled by 1043 steel potential. So we call it structureless carbon sleeve shape pore. So with this Fc function, we are able to construct the integral of the pressure tensor using 10 different contour definitions. But I have to mention that the contour we are constructing here is in 2-dimensional space. When we map back to the 3D dimensional space, there are infinite number of 3D contours can be mapped to. So although I'm showing you 10 different functions here, we are basically looking at infinite number of contour definitions in 3D space. And as expected, that different contour, they converged at the same point, as you can see here. And from this convergence point, we can define the effective thickness for each layer, and the pressure tensor and the coarse-grain pressure tensor can be calculated by averaging the local value over this delta Z1 region. So this is how we overcome the non-uniqueness of the local pressure tensor. Okay, so to summarize the first part, that I have introduced what is the local pressure tensor, and it is just a second rank matrix, and it contains the pressure component in different directions in homogeneous systems. And I've shown you that the mechanical approach, which is derived from the fluid mechanics, is basically equivalent to the thermodynamic approach, which is the approach we are familiar with. And both approach suffers from the non-uniqueness problem of assigning a force to a space, or assigning an energy at a point in the space. And we are able to solve this problem by proposing a coarse-grain pressure tensor. So the coarse-grain pressure tensor is by integrating the local pressure tensor over a small space of a region. And I have shown you that this coarse-grain pressure tensor has a unique value no matter what contour definition you are using. And to support our argument, we are able to construct this contour in two-dimensional space. And that two-dimensional space contour can be mapped back to the 3D space, and there are infinite number of contours can be mapped to in the 3D space. And to the best of my knowledge, this is the first time we are able to do that. So in the second section of this talk, I would like to give you two examples applications of the local pressure tensor. So the first case is the high pressure phenomena in nanopores. And in this case, I will show you like what is the high pressure phenomena in the nanopores, and how can we apply the local pressure tensor to understand this phenomena at the nanoscale. So the so-called high pressure phenomena was recently developed. It's pretty like in the past decades, past 10 years. So the high pressure phenomena basically says a phase transition or reaction that requires very high pressure can be readily occur in a nanopore under ambient pressure. So for example, I'm showing you here that you can form a conducting sulfur chain in the carbon nanotube under the ambient pressure. So as we know, if you want to form a conducting sulfur chain in the bulk, you need like 90 gigapascal in the bulk. But if you just put the sulfur in the nanotube, the ambient pressure is just enough. And it's also possible to synthesize this high pressure crystal phase inside the nanotube. And of course, the ambient pressure is just below the 1 atmosphere. And recently, people also showing that you can actually carry out the high pressure reactions when the product and the reactants are confined in the nanospace. And this is the high pressure hydrolysis reaction confined in the two graphene sheets. So all of this phase transition and chemical reactions are performed under very mild conditions and without catalysis. And without the nano confinement, this phase transition and chemical reactions require like larger than 1 gigapascal in the bulk to happen. So people are really interested, like what's the microscopic mechanism of this high pressure phenomenon? And as indicated by the name, the high pressure phenomena, it's related to the pressure. But now the system is not a bulk, but the system is confined in the nanotube or nanospace. So we have to calculate the pressure at the nanospace. And this is where our local pressure tensor can play a very important role. So the example I'm showing you here is the nitric oxide dimer reaction. So the two nitric oxide monomer can be converted to the dimer. But if you want to reach the 98 yield in the bulk, you need 1 gigapascal in the bulk. But people found that if you confine the nitric oxide inside a carbon nanotube, even under under one atmosphere, there are over 98% yield of the dimer. So this is really interesting. This experimental observance was discovered like 1980s, and since 1994, people are trying to understand this phenomena using simulation. However, no success has been made until recently. The reason is that people usually use the classical force field to describe the interaction between the nitric oxide and the surface. But the recent ab initio calculation shows that there's a very strong interaction between the dimer of the nitric oxide or the monomer interacting with the surface. So if we describe this interaction using 12.6 nanojoules, the value of the nitric oxide with carbon atom, with the carbon surface, is about 20 times stronger than what we expected from the classical force field using the Lorentz-Berthelot combining rule. So we know this. There are really strong interactions between the sorbate and the solid, and we can carry out the Monte Carlo simulation. We used the Monte Carlo simulation in Gibbs ensemble. So what I'm showing you here is the yield of dimer versus the temperature. So you can see the experimental value in the porous state is almost like a yield is 100%, and it's independent of the temperature. And we are able to reproduce this behavior in the experiment, that in the simulation in the porous, also independent of temperature. So this is a really great discovery, because like the previous simulation work, the results from the previous simulation work that this yield will decrease with the temperature. But here we're showing it's independent and it's consistent with the experimental data. And as you can see in the bulk, that's the dimer reaction almost like there's no yield, very low yield in the bulk. So what's really happened at the nanoscale? So why this high pressure reaction will happen in the nanopores? And we can calculate this local pressure tensor inside the carbon nanotube. And as we can see that the pressure inside the nanotube is huge. It's like 200 gigapascal. And this is what I'm showing you here is the tangential pressure. So that's the pressure parallel. So this strong pressure is due to the strong surface force between the sorbate and the solid. So as you can imagine, the strong attractive force field of surface will attract the molecule to the surface, and the molecule will repel each other on the surface. And that repulsion between the molecules leads to this very high, this huge pressure. And this surface-driven high pressure can be actually very easy to see in the molecular dynamics trajectories. So what I'm showing you here is the top-down view of first layer near the surface. And from left to right, I will gradually increase the attractive force field of the surface. So from the left, the surface is really, the attraction is really weak. And to the right, there's a strong surface attraction. So, okay, let me play this. Yeah, so if you have this weak surface force, you see the molecules, they form like a liquid phase. And when you increase the surface attraction force, there's a phase transition between the liquid to the solid. So on the right-hand side, there's like almost form a crystallized phase for the first layer near the surface. And if you imagine each of the particle as a nitric oxide monomer, so those monomers, they packed closely on the surface and they repel each other, and they have this strong pressure inside of them. And that's just basically how we create high pressure in the bulk, just to compress the system, right? So this actually brings up a new concept. I mean, this concept is not new, but it's a really interesting concept that you can actually perform this high pressure manufacturing in a carbon in nano confinement without the traditional compression. So on the left-hand side, I'm showing you some traditional compression methods, like this hydrothermal synthesizer and the envious cell. So in the industry, because of the safety issue, the pressure cannot go beyond 25 megapascal. And in the laboratory, we can create this high pressure environment using the envious cell. But as you can see, the sample size of the envious cell is very small. So you cannot scale it up for the industrial application. And the concept is that you can actually perform this high pressure reaction or the high pressure phase transition inside a nanotube, inside a nanopore. So this nano reactor can be a nanotube, or can be a nano slit shape pore, or can be any suitable porous material. And the way that we create high pressure inside a confinement is different from the traditional compression. So the traditional compression is just a mechanical compression. You compress the volume to create the pressure, high pressure. But in the nano phase, the one method I'm just showing you that is through the strong interaction between the surface and the fluid. So the fluid molecule closely packed on the surface, and they create this high pressure in the direction parallel to the surface. So we call this tangential pressure. And this process is really, as you can see, it's safe and efficient. And the pressure is the tangential pressure. The pressure does not directly act on the material, so it will not force material to fail. And of course, this is a porous material. It's also very easy to scale it up. You just pack the porous material together, and you solve this. You optimize the transport and the reactions inside nanopores. But I have to say that this green route is still in its infancy. People discovered this high pressure phenomena, I think it's 10 years ago. So this is still a very new area, and people need to look at this, the microscopic mechanism of this high pressure phenomenon. And actually, one obstacle to the progress is that the fundamental problem of the thermodynamic variables at the nanoscale. One example is the local pressure tensor, because the pressure tensor is non-unique at the nanoscale. And that's actually prevents us to from studying the mechanism in the nanopore. But I think we have made some progress right now, and we are positioned to the right in the right direction. And the second case I'm showing you here is we're using the microscopic pressure tensor to study the mechanical profile of the solid nucleus. So the pressure, what I'm showing you here is the pressure is a more sensitive property than the density to detect some defects in the solid. So this is the collaboration with the Pablo Montero de Harris and the Carlos Vega at the Complutense University of Madrid. So nucleation is universal in our daily life. So you can see the nucleation of snowflake. That's just the phase transition of the water molecule from the liquid to the ice. And in the industry, we have in the production of chocolate or the production of drug, we also need this nucleation from the liquid to the solid. And in addition to the solid liquid nucleation, we also have the gas liquid nucleation. So one example here is the CO2 bubble inside the glass matrix. So this gas liquid nucleation, sometimes we also call it cavitation. So to understand this nucleation process is very important to the manufacturing and also defrosting and many other applications in our daily life. So in the past decades, one of the most successful theories is the classical nucleation theory. So classical nucleation theory describes the Gibbs free energy cost to create a crystalline in a metastable phase. So the key component here is the delta G. That's the energy barrier to create a critical nucleus. So if you look at the equation of the delta G, it is closely associated with the property of this critical nucleus. And once we know the delta G, we can calculate the nucleation rates and many other properties, which is key to the nucleation process. So as we can see here, to understand the critical nucleus is very important. And the typical methods to model the critical nucleus in simulation is through the seeding methods. We call it seeding technique. So in a isobaric isothermal ensemble, NPT ensemble, where you fix the pressure and temperature, you just insert nucleus into a supercool liquid, and you simulate various temperatures. And during this process, you monitor the grow and shrink of the nucleus. So for the critical nucleus, it has 50% percentage of time to grow the nucleus. So the 50% of percentage to grow the nucleus to the solid, and there are 50% to shrink to the solid to the metastable liquid. So by doing that, we can simulate the critical nucleus. And very recently, the Carlos Vegas group was able to simulate this critical nucleus in a canonical ensemble, NVT ensemble. So we are able to simulate this critical nucleus in a supercooled hot sphere fluid. As you can see here, the snapshot of the critical nucleus inside a supercooled hot sphere fluid. And if we look at the density profile, this is density profile versus the radial distance. So R equals 0 is the center of the nucleus, and R equal to 30, that's the outside supercooled liquid. And from this density profile, you see there's nothing strange. Like, as we know, the critical nucleus is a solid, so the density must be higher inside than outside. And like the common sense is that the critical nucleus is similar to the bulk solid. So you can basically apply the equation of state of the bulk solid to study the critical nucleus. And that's the common sense. I mean, it's the previous common sense. But now, the strange thing is, if we calculate the pressure tensor inside this system, that the pressure inside the solid is actually lower than the pressure outside the liquid. And this is really strange. Like, people are I think this is for hot sphere fluid, and people also observed this for the Lennard-Jones fluid like 2 years ago. So this is really we are really curious that why is that? Because if you have a lower pressure inside the solid, that's not the bulk phase, because the bulk phase must have the higher pressure inside than outside. And this actually prompt us to study the structure of the critical nucleus. And we found that the reason is that the critical nucleus has a different structure than the bulk solid. And the bulk solid, as you see here, is I'm showing you the FCC structure here, and the middle is the bulk solid with vacancies. And the actual structure of the critical nucleus is an expanded version of the bulk solid with vacancies. So this is a very interesting observance, but we are still trying to understand deeper why the nucleus is forming this kind of structures, and this is still an open question. So to summarize these two examples, in the first case, I'm showing you the high pressure phenomena in the nanopores, and I showed you one example, that's the nitric oxide dimer reactions, and we see that the conjectures based on the microscopic pressure tensor can help us understand what's really going on inside the nanospace. And the second case is that we study the mechanical profile of the solid nucleus. That solid nucleus is the critical nucleus in the classical nucleation theory. And we found the pressure is actually a more sensitive property than the density to detect the defects inside the solid nucleus. So this work will be impossible without the support of many of my collaborators, friends, and of course, most importantly, my PhD advisor. So now I would like to thank them for supporting over the past 5 years during my PhD. And if you have any question, I would like to ask. If you have any question, please ask them, and I would like to answer any questions. Thank you very much.
Thank you so much, Professor Shi. We are now open for questions. If you want to ask one, please enable your microphone. I would like to remember that our YouTube viewers can also ask questions. So who wants to be the first?
Can I start?
Go ahead.
Thank you, Chief, for this nice presentation. I love these results. I'm very basic question is this not unique pressure tensor is you need the heterogeneity of your fluid, or even for homogeneous fluid you find this?
Oh, so like in the homogeneous phase, there's no such problem. So as we know, like in the bulk phase, the pressure is a scalar, and there's no problem because according to the classical thermodynamics.
Yeah. Okay. So that's just to be clear in my mind. So you are saying that this formation, well, as we have a kind of heterogeneous medium, and you need some correlation in size to get the pressure. So it comes from this correlation in size. So you need a minimum size in order to have kind of good information, is it?
Yeah, that's right. Yes, yeah.
So let me ask you something. If you have another thermodynamic properties like dielectric constant, you need some correlation in some polarity of vectors.
Mm-hmm.
So do you think that the same is going to happen in other kind of properties like dielectric constant inside the nanopore?
I'm actually, to be honest, I'm not an expert on the dielectric constant, but this problem also happens to the volume. So actually, when it comes to the length scale that close to the size of the molecule, so it's really hard to define that length scale like uniquely. Like what's, like for example, like what's the size of the molecule? Like people using van der Waals radius, but that's just like I think it's a semi-empirical way. There's really no like rigorous definition of what the size of a molecule. So this, I think this is natural because when it comes to the scale that close to the quantum size, And I think what we're going to do in the future is that we want to find that the limitation of the thermodynamics at which length scale, like maybe at like below the 1 angstrom, the thermodynamics doesn't work, or below any like a length scale. So I think finding the limitation is what we are going to do.
That's exactly my questions. Okay, I understood much better now. I agree with you, and maybe you have to think about what locals mean when you're talking about thermodynamics.
Yes, yeah.
Okay, thank you very much. Let people ask answer, but I have some question more, but let people ask first.
I have a question, Fred.
Sure.
Go ahead, Professor.
Yes. Okay. But no, first of all, thank you very much for this very interesting presentation and very interesting results that you got. My question is,
can I ask you if you can open your camera, please?
Oh, sorry about that. I saw that was open.
Okay.
All right, sorry. My question is regarding the unique pressure tensor that you have proposed, which is some kind of average pressure over a small interval.
Yeah.
Does this local average unique pressure tensor preserves the invariance of the tensor invariants? You know what I mean?
Not quite.
You have the tensor, the stress tensor, for example, and they have invariants. For example, the trace of the tensor, the determinant of the tensor. So this local average pressure preserve these invariants. I'm not sure about that. Can you?
Yeah, I think so. Yeah. And actually, the cross-grain pressure tensor I'm showing you that is from the mechanical route. But of course, you can also derive the exact equation from the thermodynamic perspective. So I think that's that consistency gives us confidence on the final results.
Yeah, because I saw that you preserve the symmetry of the system. Okay.
Yeah.
And this symmetry is also regarding to the size of this distance between where you evaluate this average pressure, and this distance should always be the distance between particles, or should be any other distance that to evaluate this average pressure.
So the distance, do you mean the delta? The delta?
Yeah, delta Z1. Yeah.
Oh, so this distance is system dependent. So for a different system, you have to recalculate this value. As you can see here in the adsorption system, this delta Z1 corresponds to the effective thickness of the layer. So that's the thickness of the adsorption layer. But
so
for some other system, you have to recalculate.
So this is the most important properties for this unique pressure. You have to choose very carefully this distance. Yeah. Preserve the symmetry and so on.
Right. Yeah. I agree. Yes.
All right. Thank you very much. Very nice.
Now, just to complement this question, is it a minimum size, or so if you get some multiples for this size, you're going to have the same? So that's a minimum size that gives you unique information, is it?
Yeah. I think this delta Z1 is the minimum size that can give you the unique value. I mean, what people usually do is they average the pressure over the entire system. So that's it's the trace of the pressure tensor. So that corresponds to the scalar pressure in the bulk system. And that's usually what people usually do. So you don't have to deal with, in that case, you don't have to deal with the non-uniqueness of the local pressure. So what we are doing here is trying to find the minimum length scale that can give you the unique value. And the results are really interesting because this minimum length actually correlates with some physical property that makes physical sense. For example, here is the thickness of the layer. for the absorption system.
I'm wondering for more complex geometry, how you do that.
Yeah, that's one question that the reviewer asked. This is and I plan to do this in the future. My postdoc research is not related to this, but when I have some time, I will try to figure that out.
And while we are on this slide, if I may, I want to have a follow-up comment on this, Kaihang.
Yeah.
And it was a very nice talk. I learned many more new understandings from your slides, although I myself have been listening to Keith talking about the pressure tensor many times. So I think the contribution is really exciting. So basically, you try to tell us that normally when people talk about pressure tensor, they try to correlate the pressure tensor to the location of R, and then they try to calculate the time average. But now you tell us that we need to worry about this delta Z, right? So I think like we just discussed, is it possible that this delta Z is also connected with the density distribution?
Yeah, I've presented some results in my thesis, but they are unpublished.
Yeah.
I mean, they are published in my thesis, but not in the research article. So I studied this this delta Z, compared the length with the density profile. So what I find that is that let me go to the next slides.
I think you have this slide in this figure A. Give us this delta Z. We are moving from one location to the other. It's actually this delta Z is also changing, right?
Yeah, and you can see that basically the delta Z is from the minimum of one point to the other minimum of the density profile. I mean, roughly. It's not exactly, but it's roughly in that length scale.
Yeah. You know, while I was listening to you to explain this slide, I had a feeling this might be related with the classical density functional theory. For example, the pressure tensor is not a property of the point, but we need to look at the local structure, and the local structure of different species could be expressed by the density. The density variation or the classical density functional theory. I don't know whether it is possible, but I just had that feeling while I was listening into your talk. So
yeah, I actually don't know. What I saw is people like using density functional theory, they calculate the scalar pressure. I mean, it's still the pressure tensor, but it's not local scope. It's not local tensor. So they average the local value over the entire space. So they have the tangential pressure and the normal pressure all averaged over the entire space. But I don't know if there's if it is possible to correlate that using the DFT. But it's I think it's worth trying to look at that.
Yeah. Now you are the expert. I think you could be the best candidate to explore along that direction. Anyway, thank you, Kaihang. Very nice talk.
Thank you, Paul.
We have a question on the chat. Rodrigo Bartolomeu, would you like to ask?
Of course. Thank you, Larissa. Are you hearing me?
Yeah.
Yes.
Okay. Thank you very much for your talk, Dr. Shi. It was very good for me to take a look at this topic after some years. And I have a question regarding the method that you used and some references that I've come through the years, and I would like to know a little bit more what you know and the parallel of their work with yours. The first one is the work of Todd, Evans, and Davies.
Okay.
And about the method of planes, which I believe it has something interesting to look with too. and
Yep.
the volume average that Hayes compares to the method of planes, and for some other geometries like the subspherical, the spherical subvolume. So it's just my curiosity. I would like to know a little bit more the comparison of the methods to yours, and I would thank you if you could talk a little bit about this.
Yeah, sure. So the Todd paper, the first paper mentioned by Todd, I'm familiar with that. So that paper, mass of the plane, if you look at that paper, it's basically calculates the normal pressure I'm talking about. So the mass of the plane can only calculate the normal pressure. So that's the PZZ I mentioned here. So the method of the plane that method cannot calculate the tangential pressure, and that's that Todd paper just it's a very nice paper. It proposed a unique way to calculate this local pressure, but it focused on different topics as me. I focus on the uniqueness of the for the tangential pressure, but the Todd paper was discussing the method to calculate this normal pressure. Does that make sense to you?
Yes. Actually, at some point in my research, I needed some years ago another method to compare to Irving Kirkwood to compare the tangential pressure, and I looked over the method of planes, but it didn't answer my questions. I wish at that time I could read your paper. Thank you.
Yeah. You also mentioned the second paper, right?
Oh yeah, the one by Hayes in 2014 that he published with Smith, Danny, and Zaki, the method of plane pressure tensors for spherical subvolume. So I believe it's also for the normal to the radial in this symmetry. So it wouldn't help a lot with the tangential pressure as well. But
Right.
thank you for your work and for the contour lines. It was very sophisticated, and I'm glad I was here to hear.
Okay, thank you very much.
We have a question on YouTube by Rafael Belém Lavrador. He said, "Hi, I really enjoyed the presentation.
Thank you.
Mr. T showed a situation in which a stress pressure was created by making the fluid go through a nanotube. Could it be possible to have the same effects with a steady fluid and a moving solid, even in bigger dimensions? What I mean is having a high pressure phenomenon happening in the surface of the moving solid, for example."
So when I say this high pressure phenomena inside the nanospace, of course, the reason I explain is that there is a strong interaction between the surface and the fluid, and but there's also the other advantage of putting the reactant or the molecules in the nanospace is that because in the nano confinement, it provides you a isolated environment. And also, there's maybe some geometric constraint to the product or the phase. So I think that also contributes to the to this high pressure phenomena. If you only have like in the bulk, like only have one surface and the moving fluid, I'm not sure, because that in that case it loses the advantage of the confinement, the geometry confinement. But like to my knowledge, I didn't realize there's any research like high pressure phenomena research about that, like without confinement.
Of course.
But of course, my knowledge is also limited. This is like a brand new area. We are still like studying progressively. So yeah, that's my answer.
If Rafael wants to say anything else, I think he will write on the chat. And here on this platform, do we have another question? So if we don't have any more questions, I think it's time to wrap it up, right?
Okay, thank you, Professor Kaihang Shi. We're going to close your slides if you don't mind.
Yeah.
For the final announcements. Thank you, Professor Kaihang Shi, for the presentation.